This video is going to cover section 1.1 of chapter 1 for business calculus or math 150. We're going to start by discussing functions. The goal of this video will be to define a function, introduce function notation, discuss functions as tables, graphs, and formulas, and then working to solve and evaluate functions. The definition of a function is that it's a rule for a relationship between an input or independent quantity and an output or dependent quantity in which each input value uniquely determines one output value. We say that the output is a function of the input. Another way of thinking about this is the input or independent variable is what goes inside the function. So we're looking at input independent goes inside the function, and the output is the dependent variable. And we want to say that for each input, there's exactly one output, or each input corresponds to exactly one output. For function notation, the notation output equals f of input defines a function named f. This would be read output is f of input. So again, if we use our function definition and vocabulary, we see that y is a function of x. Y is our output or dependent variable. X is our input or independent variable, and it's inside the function. Let's take a look at an example. The number of cubic yards of dirt, which is represented as capital D, needed to cover a garden with area A square feet is given by D equals G of A. A garden with an area of 5,000 feet squared requires 50 cubic yards of dirt. We want to express this information in terms of the function G. So for part A, we want to express the words in terms of our D equals G of A. So here we have a garden that has an area of 5,000 square feet. That gives us our value of A. And it requires 50 cubic yards of dirt. That's our output variable D. And so we would say that 50 equals G of 5,000 in our function notation. Alternatively, if we have our function notation, G of 100 equals 1, and we want to explain the meaning of the statement, in part B, we would say that a garden with an area of 100 feet squared requires 1 cubic yard of dirt. Another representation of functions could be tables of values. They can also be represented as graphs or formulas, but the idea for the definition of a function still needs to hold true, which is that each input corresponds to exactly one output. And so for this example, we want to identify all of the following tables which represent y as a function of x. So when we say y as a function of x, that tells us in that terminology that y is the output variable or dependent variable, and x is the independent variable. So let's denote that really quick just for our notes. Y is going to be the output, and x is going to be our input. So we want to make sure that for each x, there's exactly one y associated with it. So if we take a look at our first table in part A, we see that we have each individual x, 5, 10, and 15, corresponds to exactly one y. And so in part A, the table does represent a function. So I'll just put function, check. In the second table in part B, we have 5, 10, and 15, so individual. Now 10 and 15 go to the same y, but 10 and 15 each themselves only go to one y value, and so this does pass the definition of a function. So we'll do function, check. And then finally in part C, our table has 5, 10, and 10. The first 10 goes to 8, and the second 10 goes to 14. And so we have one x value going to two different y values, and so it fails the definition of being a function. And so this is not a function. This might be a little bit easier to see with a graph. So let's determine how we can identify if a graph represents a function. Before we do that, we'll look at solving and evaluating functions from a table. When we evaluate a function, it's what we do when we know the input value. and we use the function to determine the corresponding output. If we're solving the equation, we know the output and we want to find the corresponding input value. So we want to evaluate f of 3. This tells us that x equals 3 for our table. Our table, the input is x and the output is f of x, so f is a function of x. And so in our table, we go to where x equals 3 and we look at the corresponding output, which is 53. And so to answer this question, f of 3 would equal 53. Alternatively, in part B, we want to know for what x does f of x equal 1. So we'll go to our f of x row and we'll look where the output is 1 and find the corresponding x value, which will be 2. So we say to solve x equals 2 when f of x equals 1. Now we can determine whether or not a graph represents a function, and we'll do so using what is called the vertical line test. The vertical line test is a handy way to think about whether a graph defines the vertical output as a function of the horizontal input. So if you remember in words, it is a function if for each input there's exactly one output. So if we imagine drawing vertical lines through the graph, if any vertical line would cross the graph more than once, then the graph does not define only one vertical output for each input. And so if we draw our vertical line and let it pass through the first graph, we see that this hits the function in more than one place. So this would be not a function, as there is not a unique value for one x input. So it fails that definition of being a function. Now, if we let this vertical line pass through our second graph, notice that everywhere it's moving, it's only crossing through the function exactly once and no more than once. And so the second graph would be representation of a function. And finally, if we look at our ellipse at the very end here, we can clearly see that at every place, this vertical line will cross through this ellipse twice, and so that last graph is not a function. So graphs as functions can also be evaluated and solved as well. Evaluating function using a graph requires taking the given input and using the graph to look up the corresponding output. Solving a function equation using a graph requires taking the given output and looking on the graph to determine the corresponding input. So this is very similar to using a table, but now we have the graphical representation. Again, if I want to evaluate g of 2, this is telling me that x equals 2. So I want to go to x equals 2 on the graph, on the horizontal or x-axis in this case. This is our x-axis. This is going to be our g of x-axis here. That's our corresponding to y. So I want to go to 2 on the x and go up until I hit the g of x line. And then I'll go backwards and see that the output is going to be 4. And when we evaluate g of 2 using the graph, the output is 4. Alternatively, in part B, I want to find x where g of x equals 2. So I'm solving for x when g of x equals 2. That tells me to go to 2 on the y-axis, and I'll go to the left because that's where the graph exists until I hit the graph, and then I'll go down and see that g of x equals 2 when x equals -3. We also want to be able to identify the domain and range of functions. The domain is the set of possible input values to a function, what's allowed. There are going to be functions where you're going to have some restrictions to your domain, what you are allowed to plug in. The range is going to be the set of all those corresponding output values to the input values in the domain. We're going to always report our domain and range in interval notation. On the left-hand side, it's an inequality form, typically referred to as set builder, and then on the right is the corresponding interval notation. I would keep this handy for your homework and quizzes. So let's take a look at two examples, a function in formula form and a graph to determine the domain and range for the function in interval notation. So starting with the first function, which should say f of x equals 9 over x minus 6. This function will be undefined if the denominator ever equals 0, because we're not allowed to divide by 0 by convention and rules of mathematics. And so what we want to do to write the domain, because x is our input, We want to find all values that are allowed and exclude any that cause issues for us. So if we take a look at where the denominator equals 0, we see that when x equals 6, we would have a problem because we'd be dividing by 0. So we want to exclude this from our domain. And so the domain is going to be all numbers from -infinity to 6 with a parenthesis because we want to exclude it. Parenthesis means not included, but up until. And we'll union that with every number from 6 to +infinity. And so essentially we're skipping over +6. The range is going to be all values from -infinity to 0, that's y equals 0, union with 0 to infinity because this fraction will never equal 0. You can take a look at the basic toolkit of functions in section 1.1 of your textbook to review some common forms of functions that we're going to be seeing and their associated graphs. Now, if we take a look at the graph in part 2 of this example, we can see that on the left side, there's an open circle, and on the right side, there's a closed circle, and so that's going to associate with parentheses and brackets respectively. So if we talk about the domain first, we're looking at all allowable t values in this case because we have g as a function of t. This function is g of t. So the domain is all allowable t values. So we go from left to right, smallest to greatest on the t-axis. The smallest value is going to be 2, but not included because of the parenthesis. And the largest value is going to be 8, and that will be included because of the closed circle. And so we'll put a bracket on the 8. The range will be all associated g values in this case because we're looking at a g-axis. You can relate that to g of t equals y if you want to think about it as the y-axis instead. And so to do the range, we'll start from the bottom, the smallest output, to the largest, always from least to greatest when we're doing interval notation. So the smallest value is 6, and there's a closed dot there. So we'll have 6 with a bracket. The largest value is +8 with a parenthesis because of the open circle. In the next video, we'll discuss operations on functions.